Problem 19. In the given figure, four particles form a square of edge length A equal to 5 centimeter and have charges Q1 equal to 30 nanocoulomb and Q2 equal to minus 15 nanocoulomb and Q3 equal to plus 15 nanocoulomb and Q4 equal to minus 30 nanocoulomb. In unit vector notation, what net electric field do the particles produced at the square center? So you have to see the diagram. So they clearly mention everything in the diagram. So here you have to see we have four charges, and these four charges are exactly fixed in a frame which form the structure of square. And each side of the square takes the value of A, which is equal to 5 centimeter. So that means if you draw the complete diagram, when you connected these things, it will exactly form like a square shape, right? And if you see the edge length of the square, all sides are equal, because if you take a square, all edges are equal. So that means this is also A and this will be also A, right? So that means the edge length in all sides are exactly A equal to 5 centimeter. And we have four charges. Each four charges takes the value, and that value is already mentioned in the question. Now we have to find what should be the net electric field due to these four particles exactly at the center of the square. So that means in this place, so let's we give the name for this point P. So that means at a point P, what's the electric field? That means the net electric field produced by these four charges. So we have to find. So this question was a little bit quite lengthy because we have to take the components X component and Y component, and after that we have to add all. Clear? So because the electric field is a vector quantity, so we have to use the components X component cosine and Y component sine we have to use in this question. So what I did, I take the same picture here. So first I am going to use this picture for X component, and then I'm going to use the same picture for Y component. For the explanation purpose, I just take these two diagrams. Now what we have to do, we have to find the electric field direction. So I complete this diagram in the square shape. So this is the square shape, and we have to find what's the electric field at this point. And here we have to bring the test charge. So point P, we have to find the electric field. So I am going to bring the test charge from the point, and before that we can do one thing. We can write the given first. So the value of Q1 here is 30 nanocoulomb, right? So Q1 is positive 30 nanocoulomb and Q2 is minus 15 nanocoulomb and Q3 here is 15 nanocoulomb, and then Q4 is minus 30 nanocoulomb. So that means the value of the charge is given. So let's we take from the point P, I am going to bring the test charge near to Q1. So what will happen if you bring the test charge from the point near to Q1, test charge is positive, and here Q1 is also positive. What will happen? It will repel. That means the electric field produced by the charge Q1 is in this direction. Am I right? Why this direction? Because the test charge is positive. When you bring the test charge from the point P towards Q1, Q1 also here positive because it takes the value of plus 30 nanocoulomb, so it will repel. So this is the direction of the electric field. Likewise, I have to take the test charge from point P towards Q2, and test charge is positive and Q2 is negative. So what will happen? It will attract. So that means the direction of E2 will be in this direction, right? Likewise, we have to do the same thing for Q3. Q3 here is positive, test charge is positive. When you bring the test charge near to Q3, what will happen? It will repel. So by that, your electric field due to charge 3 will be in this direction, right? And I have to find the same thing for Q4 because Q4 is negative charge and test charge is positive. So what will happen? It will attract, right? So this is the direction of E1, E2, E3, and this is our E4. Clear? Now let's we complete this diagram. Suppose I just make this is my line for x-axis and y-axis, because as I already mentioned, we have two components. Now I have to consider, for example, if you see this E1, we have two components. For E1, you have the sine component and cosine component. Likewise, E2 takes the value of sine and cosine component, and E3 takes the value of sine and cosine component, and E4 is also have two components, sine and cosine component. So what I'm going to do, I'm going to first take the x component, because we have to find the x component and y component separately, and then I'm going to add both together. So let's we take the x component of the electric field. X component of electric field. Clear? So we are going to first find the x component, and likewise you have to do the same thing for y component. Now you can see, and also the most important thing, from the charge 1 to a point P, the distance, let's we take r. So if you take a diagram, so I just roughly draw the diagram here. It's form of square shape, right? And here you have four charges, Q1, Q2, Q3, Q4, and we say this is the point P. So this is Q1, Q2, Q3, and Q4. What will happen? This is the distance between the charge 1 and point P. So let's take r, and here also the distance is r, and here also the distance is r, and here also the distance is r. Am I right? That means the distance is very, very important for calculating the electric field. Why? Because we know the formula electric field, which is equal to K magnitude of the charge divided by the distance square. So this is the formula. So if you want to calculate the electric field, the distance from the point where you are going to calculate the electric field to the charge, we must know the value of r. So you have to calculate many things. So now I'm going to write the x component value. So let's write the x component for the electric field. That means x component of the electric field, which is equal to the electric field for the first charge, x component, plus the electric field for the second charge, x component, plus the electric field third charge for the x component, and also the electric field for the fourth charge, x component, and all these are vector quantities. So we have to mention the vector symbol. Now I am going to substitute this formula. As we know this formula, I am going to substitute this formula here. So if you substitute, what you will get? E of x vector, which is equal to K magnitude of the first charge divided by r square plus K magnitude of the second charge divided by r square plus K magnitude of the third charge divided by r square plus K magnitude of the fourth charge over r square. So better I can do one thing. For the time being, I can erase the sign, because sign depends on the electric field, right? So I have to remove this sign first, and we have to find the electric field direction, and then we have to mention the sign carefully, because the sign matters here. So for the time being, I can delete the sign, and from the diagram we can find the sign now. Clear? So I just simply write the formula for each charges. Now let's go back to the diagram. You can see this is your first electric field. So this is your x component, because the line touched the x-axis. So this is our x component. So x component here is positive of x-axis. So that means the first one takes the value of positive, right? So here what's the sign? It's the first. Why? Because my x component, because two components you have. X component is this one and y component is this one. So here x component. Likewise, I have to find the x component for second charge, which is E2. So when you connect these, again this line will touch the x-axis. So this is also a positive, right? And if you go back to the third charge, when you connect this line to the x-axis, this is the negative of x-axis. So what's the sign? Minus. Likewise, the fourth charges, when you connected this line, it will be also hit the negative of x-axis. So this is negative. So sign matters for this question. You should not put positive for all the charge, Because electric field is a vector quantity, you must know what is the direction. So the direction either may be positive or negative. So here we found E1 x component is in positive and E2 x component is positive and E3 and E4 are negative. So now we have to substitute the value. As we know Q1, Q2, Q3, Q4 value, I'm going to substitute the value. But before that, and also we have to mention one more thing, because as we mentioned, this is the x component. So what is the x component exactly says? The x component is cosine theta. And also we must know what is the angle. If you see this diagram, so if you see the square, and when we mention this point, the angle between these is 90, right? So this is our point P, and here you have four charges, Q1, Q2, Q3, Q4. So this angle is 90. So what is half of 90? The half of 90 is 45 degrees. So likewise here also the angle is 45. Here also the angle is 45. Here also the angle is 45. Why? Because this angle is 90. So the half of the angle is 45. So that means here for the theta, you have to substitute 45. So which is 45? I can just mention the angle here. This is the 45. So that means every angle is 45, 45. Here also you have 45. Clear? So that's the reason we have to mention here theta, which is equal to 45 degree. Now I'm going to substitute the value, and also we have to find what's the value of R. So what I have to do, I have to take this diagram again for finding the value of R. So let's take this diagram one more time, and this time I can just make the diagram a little bit bigger. So let's take the square shape, and we mention, I'm going to mention the name for each corner, A, B, C, D. So here you have two right angle triangles you have, right? So either you can mention, you can find the value of R from A, B, D triangle or B, D, C triangle. That's up to you. So now what I'm going to do, I'm going to take any one of the triangle here. So I'm going to take the triangle D, B, and C. And I am going to apply the Pythagoras theorem for this triangle. As we know, the edge length is A, right? So that means this value is A. I'm not going to substitute the value right now. And this value is also A. And this value. So I'm going to consider only this triangle. So I can just take only this portion. So in triangle DBC, I'm going to apply the Pythagoras theorem. So you already know the Pythagoras theorem. And here, what's the Pythagoras theorem says from this diagram? DB square, which is equal to DC square plus CB square. Clear? So DB square, which is equal to DC square plus CB square. Now, what is the distance between D and C and B, which is A, right? So I can substitute the value here. DB square, which is equal to A square plus A square. So what's the total? Which is 2A square. And here we have DB square. What is this DB square? This DB square is nothing but the diagonal of the triangle, all right? So once you find the value of dB, because this is dB square, so once you find dB value, the half of the dB value is nothing but the distance r. You can go back to this diagram, you can see. So this, the half of the diagonal is the value of r for each charges. For each charges, the half of the diagonal values r. So if you want to find the answer for this r, we have to first find the diagonal, and then you have to divide this diagonal by 2 for getting the value of r. So here, once I just take the square root on both sides, so my dB, which is equal to a root 2, right? I take the square root on both sides. And what is this dB says? The dB here is nothing but the diagonal. Clear? And once you divide this diagonal by 2, you will get the value of r. So that means r equal to the diagonal. What is the diagonal here? The diagonal here is dB. So the diagonal divided by 2, you will get the value of r. So what's the value of the diagonal dB? A root 2. That means I have to divide this a root 2 by 2. So a root 2 over 2. When you simplify this, you can write these two like this, right? How you can write these two? I can write these two like A root 2 over root 2 multiplied by root 2. So I can write this 2 like this, right? So it's for the easiest, for the simplification, I write the 2 like this. So by that we can cancel root 2 here. So what's the value of r here? A over root 2. Clear? So now we have to substitute this value of r in the previous equation. And also we have to use the angle for cosine, because the angle for cosine here is, because we already studied in trigonometric, right? So we have to use that value. So now I have to go back and substitute the value here. And let's we take the common term outside. So if we take the common term outside, what we'll get? E of x, which is equal to I'm going to take the common term outside, k over r square. Inside you will get magnitude of q1 plus magnitude of the q2, and also sine minus magnitude of q3 and minus magnitude of q4. And then I have to close the bracket, and this is cosine of 45 degree. Cosine of 45 degree. I already mentioned, if you see this diagram, what is the angle? The angle here is 45, because the total angle between the corner is 90. So the half of the angle is 45, and this 45 is applicable for all the corners. Clear? So we have to substitute the value of charges here. What's the value of the charges here? So k over and r square. So I have to square this value. When you square this value, what you'll get? Which is a square over 2, right? So a square over 2, you'll get a square over 2. That 2 will go here, right? Because a over 2, so the 2 will go to the top. And now I have to substitute the value of q1 and q2, q3 magnitude. So the value of magnitude of the charge is 30 nanocoulomb. So 30 multiply 10 power minus 9 and q2 magnitude, but the sign I have to mention separately here because it is different, that is different. And what is the magnitude of q2? Because q2 in the question they mentioned minus 15. So what is the magnitude of minus 15? Plus 15, right? So for plus 15, 10 to the power of minus 9, and then minus sign I have to write. What is the magnitude of q3? q3 is plus 15 nanocoulomb. So I have to write 15 multiply 10 power minus 9. I have to write minus here, and the fourth charge value is minus 30 nanocoulomb. When you take the magnitude, which is plus 30 multiply 10 to the power of minus 9, and then cosine of 45 degree. Clear? So you should be very careful. This negative is not from the magnitude, because magnitude I already, you can see q2 and q4 are negative, but I take the magnitude, I write the positive number. These two are positive number, right? You can see, but these signs are come from the direction of the electric field. So if you want, I can show you the diagram one more time. We have to go back, and you can see E1 positive, E2 positive, E3 is negative, and E4 is negative. So all the signs refers to the direction of the electric field. So don't get confused about the charge. Here the charge I put only the positive value, but the sign what I mentioned here from the electric field. So now you can see plus 30 nanocoulomb minus 30 nanocoulomb get cancel each other. Likewise, plus 15 nanocoulomb minus 15 nanocoulomb get cancel each other. So anything, so inside the bracket you'll get 0. So anything multiplied by 0 is 0. So that means the electric field for the x component you will get 0. Now we have to find the same thing for y component. So for y component also the value of r is same, but what you have to do, we have to write the equation separately like this. So how can I write? So this is for x component. You have to write the same thing for a y component. So how we can write? E of y, which is equal to, I have to write the formula k magnitude of q1 over r square, k magnitude of charge q2 over r square. Because I did not mention the sign now, we have, for the sign we have to go back to the diagram again. I'm just writing the electric field formula for each charges here. So the third charge formula is k magnitude of charge 3 over r square, and then k magnitude of the fourth charge over r square. So now I have to close this bracket. I have to close the bracket, and also this is our y component. So what I have to do, I have to mention sine theta. But what is the theta here? What's the theta? Theta here is again 45, because as we mentioned here, so this 45 is the theta value. So sine theta. Now we have to see what is the sine for this. So again, I have to go back to the diagram. So if you see this diagram, you can see the electric field 1 y component. So this is our y component value, right? So it will hit the negative of y axis. So that means this will take the negative sign, and likewise E2 hits the positive of y axis, so it will take the positive. Likewise, the third charge hits the y axis positive, which is positive, and likewise E4 hits a negative of y axis. So what you'll get, you will get a negative here. That's it. So all this sign come from the electric field. Now we have to take the constant term outside. So what is the constant term here? K over r square, and inside magnitude of Q1 is minus sign I have to write, but the magnitude of the Q1 is plus 30 nanocoulomb. So when you take the magnitude, positive magnitude is positive, so 30 nanocoulomb. So I can put NC right now, because later on we can substitute the value of the power. And then Q2, here the sign is positive. What's the Q2 magnitude? Q2 is negative already. When you take the magnitude, it's a positive, which takes the value of plus 15 nanocoulomb. And then likewise for the third charge is positive 15 nanocoulomb. And then sign for the fourth charge is negative for the electric field. But what is the magnitude of the fourth charge? Which is minus 30 nanocoulomb. So when you take the magnitude, it's a plus, right? Now we can cancel the like terms. Is there any like term? No like term. So we have to add, and also we have to include sine of 45 degree. Clear? And we have to substitute the value of r, as we already find the answer for the r. So k r value is a over root 2. If you want, I can go back and show you the value of r, because which we already calculated. So what's the value of r here? A over root 2, but here r square. So you have to square this term, and you have to substitute the value here. So when you substitute the value, what you will get? A square over 2. So that means 2 will be here, and a square will come here. And inside the bracket, minus 60 nanocoulomb plus 30 nanocoulomb multiplied by sine of 45, sine of 45 degree. Now the value of A is already known, but first of all we will simplify this part. So minus 30 plus minus 60 plus 30. So what's the value? Minus 30 nanocoulomb. Minus 30 nanocoulomb. You'll get I think I made a small mistake here. So I can correct this mistake here. This is not a square here. Because this is a square over 2, right? So that means here you will get a square. Here you will get 2. Because when you substitute the value of a over root 2 here, so 2 will go to the top. Am I right? So that's the reason, because previously I write the reverse part. So this is the right way. So now I have to substitute the value. So first we have to simplify this. K multiplied by 2 over the value of A is 5 centimeter. So 5 multiply 10 power minus 2 the whole square, and then when you simplify this, minus 60 plus 30, which becomes minus 30 nanocoulomb. So nano, I can substitute the value, which is 10 to the power of minus 9, and then sine 45, we can use the calculator. So sine 45, now we have to substitute the value for k. When you substitute the value of k, what you'll get, which is 8.99 multiply 10 power 9 multiply 2 multiply minus 30 10 power minus 9 sine multiply by sine of 45 degree divided by 5 multiply 10 power minus 2 whole square. Now we have to find the answer for this. So after I substitute the value here, I got the answer here as EY, which is equal to minus 1.53 multiply 10 power 5 Newton per coulomb, but this is our y component, so its respective unit vector rotation is j cap, right? But after we find, what we have to do, we have to find the net electric field, am I right? So net electric field, which is equal to electric field in x component plus electric field in y component, right? X component already 0 and y component just before we got the answer, this one. So I have to substitute this answer, plus of minus 1.53 multiply 10 power 5 and unit is Newton per coulomb, and its direction for the y component is j cap, right? So what's the answer here? So when you 0 nothing, so we have to consider only this part. So the last answer after we add with the 0, same value will come. So net electric field at point P, which is equal to minus 1.53 multiply 10 power plus 5 Newton per coulomb, and its unit vector notation is j cap. So this is the answer for this question. Clear? That's it. Thank you.